So, long time ago, we did a two-sample t-test. What is the purpose of a two-sample t-test? What did it compare? You know, last exam is cumulative. A two-sample t-test compared the averages between two populations. So, if we had two populations, 1 and 2, and we want to compare the averages, we can either perform a right tail, left tail, or two-tail test to compare the averages. But how did we do it? We found the difference y1 minus y2, mu1 minus mu2, and we said mu1 minus mu2 greater than 0, less than 0, not equal to 0, and we performed a two-sample t-test. But do you believe in practice we'd only be comparing two populations? Always. What was one of the examples that we did? Between juniors and freshmen, something like that. Freshman and sophomore. So we just picked two, but technically speaking, we have 4 different college groups, right? Freshman, sophomore, junior, senior. That's 4 different populations. How do we compare 4 populations simultaneously? You may argue, if I have 4 populations, 1, 2, 3, 4. First you may say I'll compare 1 and 2, right? Then you'd say I'll compare 1 and 4. Then I'll compare 2 and 3. Then I'll compare 2 and 4. Then I'll compare 3 and 4. And then I'll be done, right? Yes? It's 4 choose 2, 6 different possibilities to compare them. But do you believe that that particular approach is effective? So, two-sample t-tests, so the number of t-tests that you can perform. So you can compare 1 and 2, 1 and 4, 2 and 4, 1 and 3, 3 and 4. What am I missing? 2 and 3. Right. So to do that, you would need 6 different t-tests. And we shouldn't do that at the get-go, because there is a concept of statistical power and increased error. If you directly jumped into this, you would be actually making a lot of type 1 error that we try to control at all times. Your tests will not be as powerful. But this would be done after doing something called an ANOVA, which is analysis of variance. What does an ANOVA do? An ANOVA It will compare the averages of all populations simultaneously. And the theory behind it is that you would reduce the type 1 error and you would increase statistical power. I won't get into those because, if you ever become like a statistics major or get into PhD and whatnot, you will learn more about it. So ANOVA is a more powerful test than doing a bunch of t-tests. But the issue here we can find if population means are different or not, and ANOVA is going to tell us, but we cannot identify which ones are different. So for instance, in my picture, let's say the average of 1 is 7, mu2 is 9, mu3 is 6, and mu4 is 81. I mean, we don't need a rocket scientist to come to a conclusion by looking at that. If I asked you, well, are the 4 population means the same or different, what would you say? They are different, right? So an ANOVA can tell you if the means are the same or not. So obviously, mu4 is not the same as the other 3. But it cannot tell you if mu4 is the one that is different from the rest. And how do we assess that? We take a follow-up step called an Ad-Hoc Test. I don't know if your book goes over it, I'll look into it. If it does, then I'll do it. There is another step that we would do to identify exactly which mean is different from the other means. Does that make sense? So there is an additional step. If the book does it, I'll do it too. But I don't think so. But do we get the concept? What are the assumptions of a t-test? A usual t-test. Not the matched pair one. The samples have to be
Isn't it like greater than 20? Or the populations have to be greater than 20 and the samples have to be above?
that's for proportion.
Oh, okay.
The populations have to be, think of July 4th, independent of each other. So here, it must be independent. In other words, they cannot have any sort of correlation. And The populations must be normally distributed in the sense that they cannot have a skew or bias. It cannot be there. So a similar thing is that the populations are identical in the sense if one of them is normally distributed, then every single population has to be normally distributed. Those are the two important assumptions that we need to have within ANOVA. The third one, this is theoretical. The variances can you not see? It says the variances of the populations are identical. And within parentheses, I wrote homogeneity of variances. So that is sort of a strict theoretical requirement, but in practice, they don't have to be exactly equal. As long as they're nearly identical, we're okay. In other words, one population cannot vary too much compared to another population. If it happened, then naturally you will get a false positive. You will reject the norm. And we don't want that, and that's why we have that assumption. Why do we call it analysis of variance? When I use an example, it would make better sense, but going back to my schematic, so we want to know how far each of these averages are from some center point, right? And if we can measure and quantify each of those differences, if one of them is really large, then naturally the value is going to be large. So what do I mean by that? Let's say that is the average of x1 bar, x2 bar, x4 bar, x3 bar. Good? So that's like the grand mean, which is why it's in the center. So the idea here is to see how far the first mean is from that center, how far the second mean is from the center, how far the third is from the center, how far the fourth is from the center, right? If all of them are very, very small, when you combine them all together, you will get a small number, yes? But here is the funny thing about math. When you take the average and when you add these differences, it'll always be 0. Do we know why? Take 1, 2, 3. What is the average of 1, 2, 3? 2. What is 1 minus 2? This is the average. 1 minus 2 is minus 1. 3 minus 2 is plus 1. You add them together, what do you get? 0. So the same thing applies here. If I simply added whatever differences that I find for that number, that number, that number, and that number, I would always get 0. So we won't just add them, we would rather add. So the difference between that mean and the grand mean square plus square plus x3 bar minus x bar squared plus x4 bar minus x bar squared. Right? When I do a problem, this will make sense. When I square them, the signs are going to go away, right? But the magnitude will still be the same. And if you have a really small difference to begin with, when you square that, would you get a small number or a big number? Small number, right? So if it's small from the get-go, when you square it, it'll still be small. So we add all the time, and if that added value is small, then we would say, okay, they are the same. But we can't just simply rely on this difference, rather we find this value relative to what we would call as an error due to, some unknown factor. So we will find the ratio of this relative to the error that is unknown to every single population. And if that ratio is significantly large, then the means are different. Does that make sense? So why do we call it the analysis of variance? Each of those bits right over there, there's the formula for variance. If you go back and look at statistics 2023, each of them is a variance. So that will be the variance of the first population, second, third. Does that make sense? I'll start with an example, and as I go along, I would explain each term and how it applies to a specific case. And then we should be done. Does that make sense? So you should be able to do homework in chapter 12. Yes?
Why is it that they're squared instead of just taking the absolute value? Wouldn't that accomplish the same thing?
That is a wonderful question. Do you follow this question? Why should we square instead of taking an absolute value? First, taking calculus here. No one? So one, an absolute value function is not continuous. So it's a V-shaped function, so there is a sharp turn, and that would cause problems in terms of theoretical stuff, such as finding the derivative limits and all that. Two, if I have an absolute value, for instance, we have O minus E squared over E. And I told you the distribution is chi-squared. But who came up with it? Did we just grab it out of our pockets and say, oh, this is going to be chi-squared? No. There is mathematical proof behind it as to why what we did earlier is a chi-squared. In a similar manner, if I took absolute values, that distribution is very hard to derive and for people to use. But if I use squares, then the distribution is relatively easy. It's called an F statistic and an F distribution. So we would easily have a distribution to work, which is why we don't use absolute values. But are there tests that use an absolute value? Yes. They're non-parametric tests. Any other questions? Okay, that is a good place to stop.